Just gotta make sure we get it all in order.
All right.
But yeah, just to not have the dead air here. What's everyone's favorite color? Think about that. Doesn't that make you feel good? Look, your favorite color.
All right, we got to get Toby off the air quick. All right. All right,
Are
we
we
should
good?
be we're good to go. Okay,
Okay.
so this is how the format will go. If you guys have we're going to lay out the history of Earth's motion, relativity, and interferometry, and how the ether relates and all that, or the conception of the ether at the time. And as we go through the history, we're going to break down specific instances or experiments, and we're going to talk about them, in detail. And then if anyone has any questions while we're going over them, we actually have the purple pill tweet thing or whatever, the pill thing. So if you guys have any questions, you can click that little message icon down at the bottom and tweet your questions, and we'll get to them, throughout the show. And then also while we're discussing this, if you have questions, you can raise your hand or request a mic and ask questions live. This is for people to learn and for people to ask questions, right? This isn't for if you want to come up here and like debate and be aggressive, you'll get smoked. But if this is for people to learn, right? So this is for questions and stuff. All right, so we'll get going here. Did you have anything you wanted to add, Toby? Oh, by the way, so the way that you could follow along, you can click my profile, right? And then you can see that I'm streaming this event too. So you can follow along with the visuals that'll be displayed. We don't have the like a webcam feature to show it in the thing yet, but that'll be forthcoming. But there will be stuff to follow along with. So if you guys want to follow along with what we're talking about, there'll be visuals and stuff that'll be shared. And we'll just kind of go through everything as in a cohesive timeline.
So I think we got everything, dude. Everything's rolling. You want to bring someone up?
There's not even any mic requests yet. So we're. Oh, you mean just bring? I got you.
Yeah, like
just to see how do you do that? Then mics to the boys.
Can I not send a mic until they request it? Is that for real?
So I went through the list and sent mics. So if they got mics, that'd be dope. But if they didn't, then sorry, it just doesn't work on computer. But I sent mics to I Am, Kat, Xavier, and some other people. So if you guys got those, look out for them.
I can go check for requests on the phone too if we need to do that.
I can see requests, but I don't know if I can send them.
I can go check right now.
All right, yeah, we're going to check on that real quick to make sure we got that sorted out. I Am, there we go. And then Xavier, Cage, Orwellian, Kat, Zetetic. You guys want to come up?
I definitely hit Zetetic. Nice. The dude that never speaks, come speak.
Oh, does he not speak? Oh, I didn't know that.
He sometimes speaks. Nice. That one day on Discord, he spoke, if you remember. I think.
No, not at all.
Oh, really?
No.
Evidence or it didn't happen, I guess. So it's all right, boo. I expect there'll be Globers will show up with like dude, relativity is the best and most technically proven ever done ever. And it's like, oh yeah, great, come sit down. It's gonna be fun.
Here's a bunch of GPT sources of why.
I looked and everyone told me that was the case. Okay, good, cool. Name one.
Right, so yeah, I think we're situated somewhat for now, right?
Yep, I'm just pulling up notes on Aries failure and stuff because that's about where we're going to kick off at. In a new tab. Aries, okay, so we're going to start with the history of motion and the Earth. what men try to decipher when they looked up in the sky. They tried to for years they've been trying to determine, you know, are we moving? Is the sky moving? What's our place in the universe and stuff? We're all told these stories about these experiments and these equations and these new branches of physics that explain everything, right? So this is going to be like a broad overview uh, of all of that, and then but we're going to break down each one of these. So starting back with just observational evidence that they put forward for the heliocentric model that the Earth is in motion amongst all the other things that move in the sky is they have stellar parallax. They say that over the course of a year, or I'm sorry, that over the course of 6 months, stars will be displaced in the sky with an angle that corresponds with that, or that would only be produced by Earth's motion, right? But what they don't tell you is that those angles are just triangles and they're geocentric equivalents. So if you reverse it, you would get the exact same angle, and that's completely irrefutable based on just observation, right? So there's no way to distinguish if this observation of things moving in the sky can tell us if we are moving or if the sky is moving. Here's another diagram of what stellar parallax looks like. So in the heliocentric model, what they say is that the Earth is moving around the sun, and the Earth is 93 million miles away from the sun. So they would take a measurement here in June, and then the Earth would move 93 million miles away, or I'm sorry, doing its orbit around the sun. It would be an additional 93 million miles away. So they have a 300 300 million kilometer baseline, right? So I think, what does that come out to, like 186 million miles or something like that? So they got the baseline for the triangle based on the assumed motion, and they're just applying it to the displacement in the sky in reference to what they call fixed stars, which sometimes move, but sometimes they don't, depending on the observation and what they're trying to prove at the time. So this is how they derive distances from these, right? And they say that these angles are only produced by Earth's motion. But as we just seen here, from a stationary Earth and just the motion in the sky, you would have an equivalent angle. So that doesn't tell us very much. Now, next up, we have in my opinion, what would be considered the best heliocentric proof. This is stellar aberration, 1727, with James Bradley. He was taking observations of stars. So what he was doing, and this is super pivotal because this leads into actual experiments where they tried to determine the difference between what's moving in the sky, right? So a quick rundown on Bradley. He was at around the 45th parallel. And he was taking observations of stars as they went 90 degrees above him. So looking straight up. And the way that he had to tilt his telescope, he found that he couldn't just look straight up at it and have it in the center of the telescope. He had to tilt it a little bit, right? And he was like, "Oh, that's interesting. I wonder if that's due to Earth's motion, right? Is that affecting it?" So that was like the working theory at the time. Now, over the course of a year of observations, what he noticed in tandem with that correction angle that he had to made was that the star would actually move. It would drift a little bit. Essentially, they call it aberration, but you can just think of it like a drift. It essentially drifts a little bit by 20 arc seconds. So a quick thing on arc seconds real quick. If you think about a ruler or a compass in the difference between 1 and 2 inches, or the difference between 1 and 2 degrees, if you break that down into, a third of an inch, a 16th, etc., that's the equivalent of arc seconds in the sky when they're talking about angles. So the arc second measurements would be 1/3600th of a degree. So you can kind of think about that like breaking an inch into 1/3600th of an inch. So over the course of a year, they move about 20 arc seconds. So, fractions and fractions of an inch, right? Essentially. And they say that this angle, that this 20 arc second angle, when they ratio that against the speed of light, they get 30 kilometers a second. And because this angle is produced from a cosine, they take that interpretation as it being produced by us being in the direction of motion. So they're like, okay, cool. This is positive proof of heliocentrism. Now, this is a perfect example of kinematics. This is a measurement. This really can't tell you if the sky is moving at 30 kilometers a second, or if there's a component in between us and the starlight, like ether, that's moving at 30 kilometers a second. And it can't tell us if the Earth is moving at 30 kilometers a second. But this math ratio is a measurement, and it is interesting, right? And it does give the value needed to confirm the heliocentric model. It's super interesting, right? So now we're going to step away from the starlight observations. Or does anyone have any questions so far? We just went through two of the big things that they try and use. Does anyone have questions about parallax or stellar aberration? Looking for hands, looking for anything?
Everyone likes work.
Okay, yeah. No, you're good. You're good. Shane, keep an eye out for hands and stuff and whatnot. But we'll go through
Yeah, I'm keeping
here.
an eye too.
Okay, cool. Okay, so we'll just continue on here. So now we're gonna get to the deciding factor of are we moving or is the sky moving, right? So we have here Aries failure, and if you ever want to listen to a video on Aries failure, if you go to YouTube and type Malcolm Bodum Aries failure, he gives like a 5-minute video. It's an excellent rendition of the whole thing, and it's so straightforward. When you watch it, you're going to think to yourself, "But no, I can't. It can't be that easy, right? It's literally that easy." So the premise of this experiment was that the telescope is stationary, right? There's nothing inside the telescope. It's just air. When you look at the telescope, or when you look 90 degrees up and you look at a star, you have to tilt this telescope a little bit to keep it in the center, right? So is the Earth moving or are we moving? So based on that tilt angle, you can't tell. But what Airy did was they realized that if you fill the telescope with water, that medium will slow the light down such that if the Earth is the cause of the displacement, then you'll have to further correct the telescope, right? Because the amount of the amount of time in which light is traveling through the telescope is slowed so much that the additional variable of Earth's motion comes into play, and it's going to require that additional correction. Now, if the telescope is filled with water and it doesn't require any additional correction angle, excuse me, that means that the starlight is already coming in at that angle and it's apparent, right? And even in their model, the starlight's apparent because the stars already happened billions and zillions of years ago, and we're just receiving the incoming light in perpetuity as little fine focused dots, right? So they, even in the heliocentric model, these are apparent positions, and they're analyzing the light spectrum from these apparent positions. So when you look in the sky, that starlight is already coming in at that angle. That's what this experiment proves. Now, this is touted as Airy's failure, and people will say that, well, maybe he was trying to detect the ether, and he failed to detect the ether. That's what the failure was about. I think if I pull up Wikipedia here, we can learn all about how he failed to detect the ether real quick. Airy's failure. Wikipedia. Where's Wikipedia at when you need it? When you need Wiki to be the first result, it's like, who's that? I don't know. All right, Aries fit doesn't even come up. But anyway, when you look into it, they'll say it's a failure to find the ether, right? So anyway, we'll read through the paper and decipher if that's truly what is claimed here. So someone's hot micing, probably Shane. So the angles that he measured, right, over the course of a year, only required a 0.8 second arc, or 0.8 arc second correction. So you know how we were talking earlier about an arc second was 1/3600th of a degree. So this is even smaller than that. This is even smaller than that, dude. So it required a slight fraction of a degree correction, a fraction of a fraction of a fraction of a degree correction. And the hypothesis was that they were going to need to tilt the telescope by 30 arc seconds. So significantly more than what they had to tilt it by, right? So in the paper here, it says, I think myself justified in concluding that the hypothesis of Professor Klinkerfues is untenable. Had it been retained, the aberration employed in the corrections would have increased by 15 arc seconds and minus 15 arc seconds respectively, and the mean of the two results would have agreed by 30 arc seconds. So the hypothesis was that the ether was stationary and starlight propagated through it. And when you filled the telescope with water, either Earth's velocity was going to require you to tilt the telescope further, or the starlight was going to remain the same and it wasn't going to require a correction, or which would mean it already comes in at that angle. And then, like I said, they added a 0.8 arc second correction, which you could interpret as evidence for an ether drift. But that's like a secondary thing. We're not here to argue that necessarily. But there was a slight correction that we will definitely be using, for our argumentation. But that's not the purpose here. Okay, so that's Airy's failure. So that's it in a nutshell. So that was Professor Klinkerfuse's hypothesis. Now they say that this was failure of the ether, remember. Now the ether in this was just the placeholder for electromagnetic propagation to take place, right? It wasn't the causal mechanism of the displacement, right? So the velocity component was supposed to be due to Earth's motion, not due to, it wasn't a detection of the ether. It was a detection of Earth's motion.
Alan, quick question.
For any specific motion?
What's that?
Was that for any motion or a specific motion, orbit around the sun, or this?
Yeah, so specific motion. The implication would have been the orbital, and it would have implied that the Earth is the thing that's moving and the sky isn't. You know how they say that like the sky changes because we rotate once a day, and also 365 days there's like the annual displacement. So this would remove the orbital mechanism as the cause of that displacement, because these are observations over the course of a year where they were trying to determine that relationship with Bradley's observations.
How does it differ from Michelson-Gale?
So Michelson-Gale was using an interferometer, so a laser beam that was split on the Earth. So this
So it's just a source that they were using?
Yeah, essentially. And then in that, they weren't looking for the orbital velocity per se. They were looking for the sidereal rotation.
What's up with that? What is it? I forget how to say his name. Lorentz or whatever calculation equation.
Oh yeah, Lorentz, dude. Yeah, we're definitely going to get into Lorentz transforms as we progress through here, and definitely Michelson-Gale Pearson as well. It's all on the timeline of events that's going to be covered tonight. Absolutely.
Alan, to be specific on this, so we see a lot of revisionist history with the measurement of the ether put claim to be for these experiments. But if the ether then was presumed to be stationary and it's matched with the lab frame of the experiment, how is the displacement happening? Wouldn't that necessitate some type of motion?
Yeah, so that's where we argue for an ether wind, right?
Yeah. But they're trying to get rid of that. So
yeah. So here's how they interpreted it. They just never talk about that, and that's it.
Nice.
So here's where it gets worse. Thank you for bringing that up, Xavier.
Is this where the atmosphere moves with the Earth and stuff, or they say
close? It's about to get way worse because of what Xavier just reminded me of. So to reconcile this measurement here, I totally forgot about that. So this is super important here. So to reconcile this measurement, right? This was supposed to be confirmation of the heliocentric model in a dynamic way, right? The other things were kinematics, they were measurements. This was an experiment. This was to test the dynamics, like the velocity component of Earth, right? In the experiment, or what I mean by experiment, like introducing an independent variable. So they introduced water into the telescope to see if that would affect the dependent variable, which would be the correction angle. Right, and then you would go from there to decipher how that aligns with your hypothesis. Is the Earth in motion, or is the starlight already coming in at that angle because it's apparent? So, okay, so listen to how they reconcile this. Right, they don't really talk about it. They say, "Oh, Airy's failure," and then they just let everyone draw their own conclusions. This is from 1887, Michelson-Morley, from the Michelson-Morley paper on the relative motion of the Earth in the luminiferous ether, where he goes over his interferometry experiment. But before he gets to that, he talks about Airy's failure or Airy's success, depending on how you look at it. And we're going to read the solution to Airy's failure for the heliocentrist. Okay. So, but it failed to account for the fact proved by experiment that the aberration was unchanged when observations were made with a telescope filled with water. or if the tangent of the or if the tangent of the angle of the aberration is the ratio of the velocity of the Earth to the velocity of light, then since the latter velocity in the water is 3/4 the velocity of in a vacuum, the aberration observed in the water telescope should be 4/3 its true value. Right, and then we'll zoom in a little bit here. This is hard to read. Then he says on the special note here, it may be noted that most writers admit the sufficiency of the explanation according to the emission theory of light, while in fact it is even a greater um, while in fact the difficulty is even greater than according to the undulatory theory. And the undulatory theory is the theory of light being a wave, right? So the emission theory, and they had like a ballistic theory or whatever, where they thought it was like a little corpuscle. But Arago had proved that, like, he puts forward significant evidence that light was a wave when he shot a coherent light beam into a sphere, and the way that the light diffracts around the sphere and recombines, it produces a dot perfectly behind the sphere, which would be impossible if light was a corpuscle. It wouldn't, or if it was like there was little particles, it wouldn't look like that. So at this time, they had changed from that theory. Everyone was pretty much on board with the undulatory theory, which just means that, vibration, right, waves. So for the emission theory, so for the lads that still believe in the particle theory, the velocity of light must be greater in the telescope. Oh, no way. So for some reason, to explain the results of why you can't detect Earth's velocity using this method, is that when the light hits the water, if light is little tiny particles, for some reason, the light accelerates in the telescope. And therefore, the angle of aberration should be less. Hence, in order to reduce it to its true value, we would need to make the absurd hypothesis that the motion of the water, that the motion of the water in the telescope carries the light in the opposite direction. And that's for the undulatory theory's position. So to explain this, what was proposed was from Stokes and Fazal at the time, right? They wrote to Airy and they were like, "Hey, bro, so you know how we're on that stationary ether grind? Well, maybe there's ether inside of the telescope, and that ether is moving around and it's carrying the light in the opposite direction of motion for some reason." And that's the explanation that they give for Airy's failure. That's why when you look up mainstream explanations for Airy's failure, you'll never hear anyone tell you about how they reconciled it. They'll just say, "Oh, he didn't measure it. He failed." And that's it. No. To reconcile this, it's ridiculous to maintain that belief system. Any questions, comments, or concerns?
I don't have anything like that. I just wanted to let you know, Alan, I added that video that you referenced about Aries failure up to the jumbo. That 5-minute video was up there.
Oh, nice. Thank you. Yeah, that's Malcolm Bodum. He does a really good video on it. I'm actually going to make a modern one because this video is a little dated, and and I don't think he touches on the explanation that they ended up giving, which is crucial for embarrassing the heliocentrist.
Yeah, and I would just really quickly like to point out that uh, anyone that's interested in the stars and stuff, like, I mean, it's called a failure for a reason. And it was the first time that they went to go measure the motion of the Earth. And or, to see what was motion, right? The sky or the Earth. It was like a definitive experiment. And they didn't measure it. So even if there were new theories now that were to explain it, which when you look into this one, there really isn't a very good explanation. But why you would have to kind of ask yourself, maybe, at least me, I asked myself, why had I never heard of this before? Why did I just learn of both of these great field experiments, Aries failure and the Michelson Morley experiment? Why did I never hear about either of them until I went and looked and dug and had to, luckily there was other people that had pointed out these things for me to find, but it's just kind of crazy that our institutions would make all these assertions without ever providing us any such of this counter evidence. This is direct experimentation showing, what's happening in the sky, what's happening with the movement of the earth versus the movement of the sky.
Yeah. I'm sorry. What was that last part you said? Determining the
Just
movement of the Earth, of the what?
Just no, just saying that it's crazy that they wouldn't want to educate everybody
I'll give
on this
you
first measurement.
yeah, to
That's all.
give yeah, to
I was
give
just
you
being redundant.
no, yeah, to give no, to give us the full history and context on it. Yeah, because most people look into it, you read the paper, they're like, okay, untenable position. That's about it. They're not like, oh, dude, that must mean the Earth's stationary, right? You got to remember, these people were all Royal Society members. They all have a strict belief system that the Earth is in motion, right? So they're not gonna, openly publish that or write about it, right? Even if they did think that. Um, but they put the data out there, and you can interpret that for yourself. Like it's pretty obvious. So, all right, so I think we're ready to move on to interferometry now, unless there was anything you wanted to cover, Toby, from Aries. Other than that, I think you already
No,
summed up.
no, I think that's great. Oh, I just would point out one other thing on this. It's a little bit off topic, but it's just good to keep in mind when we're talking about things like astronomy, that this also means that when we see the stars, they are not where we see them. They are already the light has already moved when it's gotten to us, is essentially what this means. And so that means that we see the stars in an apparent position relative to where they would have been in the rotation in the sky. But yeah, so I think that's just important to consider when we start talking about the way that all of our measurements of the globe, quote unquote, are all taken from sky observations.
I was told a gyroscope can stump all those things, and we can prove motion with the gyroscope or something.
Yeah.
Yeah, we can get into that later, maybe.
All right. So let's see. We're about to get into Fazal because that's going to lead us into our first interferometry experiment, I think. So, okay, so after continuing on after the Aries situation, right? We have the Fresnel drag experiment. And what old Fresnel did, what year was this, Toby? Oh, 1849. So in 1849, what they had found was, this is, if you're able to see this diagram, this is, or if you can, actually, I'll tweet it real quick. Somebody can put it in the Yumbo. Well, maybe I should do it like that and then just break it down from the Jumbro. What do you think about that? Anyway.
Yeah, that seems good. I can pull up my jumbo on my stream as well.
Cool. Okay, yeah. So we're looking here at a diagram, or it's a rough diagram of the Fresnel drag experiment, right? And this was done by a man named Fazal, not even though it's called Fresnel drag. But anyway, Fazal, what he did was, or what they found was, you could take sunlight, use a beam splitter, so just a crystal that's half silvered, right, and it'll split light so that it goes in different directions, and then you could use mirrors to change the direction and have it complete a circuit. So what they did here is they set up a square where the light beam is split such that it continues on this path in the blue here, and then it recombines at this beam splitter where it makes a pattern on a wall, right? Where you can look at the fringe displacement. So the other side of the beam splitter for the beam is it goes in the opposite direction, goes down, hits a mirror, continues on, and gets recombined with that first mirror that was split. And what should happen here is, if the speed is, now this is filled with water, but let's just if this isn't filled with water, right? What should happen if the speed of light is the same is that there should be no pattern produced here. The light beam that's split should recombine in phase, and there shouldn't be any displacement. Now, what they found was, when they add water to the tube and the water is traveling at a velocity through the tube, that the light rays will be traveling with and against the tube in the configuration that they have. So they have an exact velocity on how fast the water is flowing through the tube. They have the velocity of light from Maxwell's equations. So they have an estimate on how fast light should go. And they have their before and after readings where they're doing controls for their fringes. And what they showed was that that the waves are out of phase proportional to the velocity of the water. right? So when the light beam is traveling with the water, it gains velocity. It travels faster than what they have on their projection for C should be, the speed of light. And when it's going against the flow of water, it travels slower. And when it recombines, it's out of phase proportional to the total sum of that velocity going with and against it. So if you look at accounting for refraction, right? Let me pull up the actual diagram. So when you account for refraction, right, you have like 75% reduction to the velocity, but then you have an 88% proportional velocity with the speed of water. Now you're losing. The reason it's not 100% is because it's losing from the refraction. But the fact that they've measured the 88% of the velocity displacement, or 88% of the velocity through that displacement, shows that their hypothesis that the ether would be carried by material media in motion, and electromagnetic waves that were going through it would be carried with it, and they would get that velocity boost, similar to traveling with stream or going going with the stream or going downstream. All right. Any questions, comments, or concerns so far?
I'm just interested how they're going to bring back an invariance in C after that. But go ahead.
Oh, dude, you never heard of relativistic Doppler shift or whatever they tried to do? Yeah, it's nuts. They can't have this either. So
It's funny, yeah,
here's what they did, Xavier. They said, hypothetically, if this existed, this is how we would give a relativistic explanation, but it doesn't, so we don't have to. But they go ahead and do it just in case.
Yeah, and it's funny, man, they still write papers to this day with, like, relativistic apologetics for Fresnel drag. Like, the dude debunked relativity back in 1831, and Fresnel came up with the math for it before Fizeau did it, like, 20 years prior. Or no, it was, like, what is it, like, 40 years prior or something like that, but, yeah, so the guy figured out, what was gonna happen with light way before Einstein said it was gonna be constant. But, Einstein just came along and said that anyways. And I like to throw that in there, right? Because I like to say relativity's been debunked like at least 3 or 4 times. I mean, like just through I mean that in a purely paradigm way, right? Like the paradigm of relativity should have been debunked like 3 or 4 times. Like experimentation, it'd be way more than that because it would be like every single time that they try to measure the speed of light and then they calculate out the periodicity. But yeah, in any case, this would have been like the first time. Like this is the first time that they debunked special relativity, but it's funny because it's before anyone even accepted special relativity. But I guess people were just there were plenty of prestigious scientists at the time that did stand up and come out against what Einstein had to say. A little bit sidebar from this conversation, but yeah, so that's just something to consider that they're still writing apologetics for the fact that the speed of light goes with or against the flow of the water.
Well, but this was prior to MMX, and they didn't get rid of the ether yet. Do they retroactively go back and correct for Maxwell? Because they acknowledge needing to go through a medium for the electromagnetic wave. Do they retro or no?
So on Tuesday, we'll find out how they retroactively removed the ether by quantizing the photon. So, like that's how they did away with that little number. But like they never really got away from it until the Compton scattering. So, which we'll get to Tuesday, and then hopefully we'll touch on that again on Friday. So let's see. We got mic requests here. I'm gonna go through real quick. Brenda, no thank you. The lad. I think I can get everybody. All right. I got everyone, I think.
Yes, hello. Toby got into it a little bit about the speed of light. Is it true that we've only measured the two-way speed of light, and how would that affect these observations?
Fantastic question. So, for the speed of light, they give us Maxwell's equation, which is an equation regarding induction relative to a electric permeability and a magnetic permeability. Now, what they tell us is that, okay, well, we only have two-way measurements, blah blah blah, and in mainstream science, most people will deny one-way measurements, etc. But that's because they have to. They're adhering to relativity, and they don't want to risk getting falsified. So the one-way speed of light has been measured. You can measure it through phase conjugate mirrors, and additionally, it's measured in GPS through the signal propagation and timing, and it reveals that the distance derived is based on a proportional relationship with the velocity of the observer. So like if an observer is on a train and they're going, XYZ miles per hour, the delay in signal propagation to derive their distance is proportional to their velocity. So you could, like, if you're familiar with the Sagnac effect, which we'll get to later, you could do a one-way phase conjugate mirror experiment of that and show that the light is already changed speed before it hit the mirror to reflect back. So we do
Well,
have. Sorry, go ahead.
I was just gonna say we should probably just maybe jump ahead. Let's just make sure we cover MMX, because everything we're talking about, just in case, because we're a little bit in the weeds, and I just want to make sure that anyone that's listening here can understand that, uh, or maybe I'll just say it like this real quick. Uh, the speed of light, this velocity proportionality to the speed of light is not supposed to exist in special relativity. In any of Einstein's paradigm, the speed of light is supposed to be the same, constant in all reference frames. And if that's not the case, then that means we can use the quote unquote speed of light to measure the orbital velocity of the Earth, the speed of the Earth on its orbital path. And actually, we should be able to pick up the cosmic speed as well. But uh, so that's why this is so important to this discussion about motion.
Yep. And yeah, we're actually right about to get into Michelson-Morley. So this is the crux of measuring translational speed, right? So what they demonstrated here is that you can use light to measure translational velocity. So the water that's moving through this pipe produced a 88% proportional velocity variance in the speed to produce those fringe patterns that they measured and derived that relationship with. So this was a huge moment for them, because this was like discovering, I don't know, I can't think of an analogy right now on the spot, but this was huge, because that meant that you could use light to measure motion, right? The same way that you could use sound waves and water to derive distance and stuff, right? And the velocity of an observer, how it'll change relative to them in the medium, right? So it was like, this was huge for them. So this is why in 1881, they did their first attempt, but the apparatus was too sensitive, blah, 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 right? But in 1887, Michelson-Morley came back, and I'm pulling up the paper now that we can get into it. And they were going to test the velocity of Earth through the cosmos this time. So before, maybe the telescope was, maybe the ether was trapped in the telescope and it was carrying the light in the opposite direction. We need a redo, right? So we're going to use Michelson-Morley as our second rendition of measuring Earth's motion. Well, third rendition, actually, because we didn't cover Arago, but whatever. All right. So we already read page 1 here of explaining Aries failure, right? In that relationship and what they have to believe in to maintain their belief. So let's see, from the first experiment that they did, Lorentz actually wrote in and had some critiques and stuff, right? And he was like, hey guys, maybe you should consider for this experiment too, that because the Earth is in motion, maybe the apparatus's length will be changed, because the Earth is like moving underneath the electromagnetic propagation, and it's effectively extending the length of the apparatus. So that's where we get into what they're talking about here with these diagrams, and this is showing like what Lorentz is conceptualizing or whatever, right? So they get here to the math derivation of how they're going to break down the measurements and how they're going to derive the velocity here in relation to c. And what they determined was that Lorentz's distance approximation of the apparatus changing was not valid. It was negligible. So they neglected that term, and then they get into how they actually do it, right? So 2d v squared over v. where the big V is the velocity of light, which is now c in modern times, and then the little v is the velocity of Earth's orbit. So they put 30 kilometers a second in that one, and then the distance would be the total distance that light has to travel from this smear or from this source all the way to the what do you call it? The photographic sheet where they were taking the measurements. So this whole path where it hits this mirror, reflects back, and travels all this way. So that total path, and it's split, right? So that's why they put the 2 in there. So they got the there and back. 1 second. All right, so they got the distance for that, and then from there, it's just the ratio of the velocity of light over the the velocity of Earth over the velocity of light, which gives them how much the fringe displacement will be in relation to the measurement for what they expect in regards to a velocity of 30 kilometers a second. And they determined that the expected fringe shift would be 0.4 fringes. That would be the distance in the displacement pattern. So when the waves recombine, there's going to be a distance between them. They'll be out of phase by this distance, and this distance will be proportional to a velocity of 30 kilometers a second. And that's how the math on that works. And then how it works mechanistically, right? You would have let me show you a better view of the apparatus here. Here's like a side view of it. Okay, so they have a cross configuration set up where light beams are going orthogonal to itself, and then it recombines where they take the fringe reading, and then it's configured on a concrete slab, right? A thick concrete slab that's sitting at a vat of mercury that they can turn, so it floats really easily. There's not a lot of there's like no resistance. And they turn this apparatus very slowly, and as it's turning throughout specific times of the day, when in the heliocentric model, the Earth would be aligned with the where you would be going into that orbital motion, that orbital plane, where you would be where you would get that light drag, right? If the ether was stationary and you were dragging light like that, like that's where it would be produced at specific times. So like that would be your independent variables, the time of day with respect to the orientation of the device. And with that, that's how they took their readings. So is there any questions on how they took the readings or what they were trying to do or anything like that?
Nothing here.
All right, cool. Let's see here. Back to it. Okay, so the device there, they got topographical view. So that's just what it looks like. So we'll get to what they measured, right? So remember how I was saying different times a day and, different days, that would be their IVs. And then the measurements that they got were just over 1 fringe. So if we look at the dotted line, this is the projected amount for heliocentrism to be true, for them to get that proportional velocity relationship measurement that they so badly coveted. And they didn't get it. Okay. So they got just over 1 fringe, which corresponds to a velocity of about 6 kilometers a second. So they needed 30 kilometers a second, and they got 6. So we'll read here for their conclusion and what they talk about. So it says, but since the displacement is proportional to the square of the velocity, and the relative velocity of Earth in the ether is probably less than 1/6 of Earth's orbital velocity, and certainly less than 1/4. So he's talking about the measurements made in relation to heliocentric model versus what they measured. In what precedes, only the orbital motion of the Earth is considered. So this experiment, the way that they conceptualized it, the hypothesis, the math, everything was derived on just the motion of the Earth. It wasn't dependent on, per se, the velocity. Like, okay, so how you could look at it through the Earth and Sun are moving with we're moving in the galaxy, so there's an additional velocity component of like 1,000,000 miles an hour, et cetera, that kind of thing. So they're saying that the derivation here in the experiment was just designed for that one velocity, for the 30 kilometer velocity. So he's just being specific about that. If this is combined with the motion of the solar system, concerning which little is known with certainty, the results would have to be modified. So he's saying, like, we really didn't even know like what would happen if we would get a bigger reading, a smaller reading. We're just trying to figure things out. And if it is possible that just the resultant velocity at the time of the observation was small enough, and the chances are much against it. So they're saying that, well, if we didn't get a huge swing like the in the fringes, meaning that the velocity wasn't extreme, so we probably didn't detect the motion of the solar system as well, right? We probably didn't detect that galactic speed or anything like that. And then it says this experiment will therefore have to be repeated in intervals of 3 months, and thus the uncertainty will be avoided. So that would be in relation to what Dayton Miller later continued doing, right? So he started taking observations on the equinoxes because in the heliocentric model, right, if we're moving on an elliptical orbit, we're going to have to change speeds, albeit it won't be a lot, but that's when the velocity changes should be happening. So that's when you should get fluctuations. That's when you should get more of that swing to see if you're actually moving with the galaxy or if you're moving with the sun, et cetera, right? But keep in mind, the velocity that they did detect, 6, and they needed 30. And these are, 1 second. It appears from what all precedes reasonably certain that if there be any relative motion between the Earth and the luminiferous ether, then it must be small enough to entirely refute Fresnel's explanation of aberration. So if we remember Fresnel's explanation of aberration for Airy's experiment, it was that the ether in the tube travels in the opposite direction of motion, right? So untenable positions to hold here. And he's saying if there is a velocity component, it would have been too small to refute Fresnel. So yeah, not sure. So let's see. That's pretty much it on that. And then Lorentz had some stuff to write in about that he included. And that's why he talked about that stuff at the beginning. So he included what Lorentz wrote to him, and this is just schematic stuff and critiques on the apparatus itself. All right. Any questions, comments, or concerns?
Yeah, being that they found a factor of 6 in velocity, not the 30 that they were expecting, how then would they conclude a constancy of light? Because there's still fringe expected. It's not null. It's not nothing. It's just a null hypothesis. How do they go?
I'm glad you asked, because this is the segue into special relativity. So this result was obviously puzzling to them, right? Because they had established already experimentally that they could measure translational velocity with light, using an interferometer. So using an interferometer of this size was supposed to be, they already knew what they were supposed to be measuring, or what, had the expected value of what they were going to get. And they didn't get that value, and obviously it's pretty small. So they weren't sure if they should if they take it as is, they can't use heliocentrism, right? Because this would be first order measurement. Now in their interpretation of a there and back speed of light, it would, at the time, it would be considered a second order experiment or measurement. But the velocity measured for them would have been significant. So they didn't really know how to handle it. So that's why several theories were put forward using ether contraction to put forward the position that, well, the Earth's in motion, but it would have already contracted in our frame, so we can't actually measure it. So what they would do from that is say that the speed of light is constant, and that 6% is just an error. I'm sorry, not 6%. That 6 kilometers is an error. Because that's actually what they do for relativity theory, right? Because yes, we can get into the explanation of that now. Okay. All right.
How much instrumental errors does have to happen consecutively for to be acknowledged?
It only when it disproves the theory is it instrumental error. When it proves the theory, you go ahead and use it. Okay. So this part, actually, let me see if I can get the image for this. I'm going to put a picture up in the jumbo. Nope, that's not it. 1 second. Right.
So touched on Miller real quick there. Are we gonna? Yo,
Oh
welcome,
yeah.
Shane.
Oh yeah. We're doing the whole thing.
Cool. I can't wait to talk about my boy Georges.
Yep. Yeah, I'm gonna let you take over here after I Lorentz transform us into the next section. I need a quick break. Okay.
Take a quick little step out of the lab frame.
Yeah, I'm gonna step out of the lab frame for a minute. Okay, so what do we got here? Okay, I put it up in the Jumbo if you guys want to see it there, or if you're able to follow along on YouTube, that'd be cool too. Or on the Twitter space through the thing or whatever. You guys will figure it out. Okay, so to reconcile this measurement, right? How doth thou explain a velocity that's not measured when your model and worldview is dependent on your motion through the cosmos? And you just realize that you took a measurement and it doesn't exist, right? That velocity that you believe in, right? So one of the frameworks put forward was from Lorentz and Fitzgerald. And what they put forward was a contraction mechanism to explain physical contraction of an apparatus in the direction of motion. So this is saying that the ether, when a body is moving through it, is physically compressed proportional to its velocity through it, right? Thus making it impossible to measure any velocity. Now, to do this, you need to do a coordinate system transformation to describe this mathematically. So this is where we get into relativistic physics, because the Lorentz transformation, the Lorentz-Fitzgerald transformation, is the same equation that Einstein uses for special relativity. Now, we're all familiar with Einstein removing the ether, he killed the ether, there's no ether, blah, 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 right? Well, his equations are the exact equations used by a previous ether theory. So how do we determine the validity of that from just that? Well, it's neither here nor there. Let's just look at the velocity stuff and what the meaningfulness is of this transformation here. So in Galilean transformations, what you would do, you would have an originating coordinate system. So you would have an X, Y, Z, and T for time. And your T would always be perpendicular to your X axis, because your X axis is typically going to be your direction of motion. So that's how that works in a graph. So actually, let me pull it up so you can get a visual on it for those watching. 1 second. All right. So I think this is going to help people, but I'm realizing now as I'm looking at it, it's probably just going to confuse the hell out of everyone, but we'll see what happens.
It's Einstein's fault. It's not ours.
Yeah. So if you kind of think about it as a graph, right? Just the familiar XYZ graph, or XY graph, sorry, it would be it's very similar to that, and there would just be a T at the top of the Y with it, right? I just tweeted a thing to the thing. If you could put it on the Jumbo. Let's see. So that's what that's supposed to represent, right? So you would have your original coordinate system, and then you would have your the coordinate system that you're transforming to, right? And this new coordinate system would be equivalent to the old coordinate system plus or minus corrections made to it. Right? So in the new coordinate system, instead of x being x is going to equal x minus velocity times time, and that'll be times the time coordinate, right? And then for y equals y, it'll be the same. Z axis is the same. T equals t, right? Now, they do have so what they do for a Lorentz transformation, right? So this is what you would do to add speed to something. Say you have something moving at a velocity of 30 miles an hour, right? And then you want to add you throw a ball out of a window at like 15 miles an hour, right? From that 30 miles an hour. Well, how you would describe the velocity of that ball, you would use this transformation to describe that original velocity and add to it, right? That's all that is, right? Now, what they do in relativistic physics is they introduce the gamma factor correction, or they call it the Lorentz, a bunch of different stuff, actually, like Lorentz something. Anyway, gamma correction is the one I'm most familiar with. So what they do here is they introduce a ratio where they ratio that velocity in time against the speed of light. I'm sorry, the distance against the speed of light. And they get a more precise measurement on it, which gives them how much that distance would contract in the direction of motion. And then they do the same thing for the time axis, because if you're going to change distance and time, you need the speed of light to be the same. And for everything to be proportional, these two things have to change in order for the speed of light to be the same. So to go with the presupposition that the speed of light is the same and you just can't measure velocity or linear motion with it, translational motion with it, is because there's contraction in the direction of motion and there's time dilation. That's how they express these things, right? This is what time dilation looks like, the T. This is what the length contraction looks like. These are ratios proportional to the velocity that they input. Now, these velocities are for really fast, quote unquote, relativistic velocities. So when you're moving, really fast, this isn't for like the example that I gave with the car and the baseball, right? That would be for Galilean. That's Galilean transformation or Galilean velocity addition, right? Now, when you get to the higher speeds, they say Galilean velocity addition still applies, right? You still have to add those speeds, but you have to use Lorentz transformations because the speeds are now relativistic. They're too fast, and you have to deal with length contraction and time dilation. So to bring this back, now that we know how the math and the mechanism answers the experiment, the way that they propose the measurement, right? They say, okay, no velocity was measured. No, they have no measurement in Michelson-Morley. It measured nothing, right? And the reason it measured nothing is because when you input 30 kilometers a second into this, you will get you will get length contraction proportional enough to explain why you can't measure it in your reference frame on the Earth, right? So you don't need to have a measurement of a velocity, but you have an explanation for why you don't have one now, right? Because this coordinate system transformation is dependent upon a velocity to produce the effect of contraction in the first place, right? So velocity would be a first order effect. A measurement of velocity where you could show that there is a exact proportional relationship with that velocity would be a first order measurement. So if you took velocity and ratioed it against the speed of light, you could show that relationship, right? So what they do here is they don't have a velocity measurement, but they just input 30 kilometers a second, right? And then they just run with it and they go, oh, look, the apparatus would have contracted by 0.00, right? And that's all they needed for it. Now, that's insane because they're using a second order abstraction, right? A second order effect of length contraction that can only be explained as a result of a measured velocity, right? They're using it as a substitute of the measurement, completely reified. Is everyone clear on what just happened there with that?
Yeah. And can I take us into Georgia's with that? Because I can really like run with that.
Yeah, absolutely. If there's no questions and we're all ready to move on, if anyone wants to rotate mics or say anything, do a hands up signal or whatever, and we'll pull you up here. Throw up some gang signs or whatever we can do. I think we can do. What emotes do we have? This one. The old hand wave. All right.
So yeah, I mean, just what you were saying there. Um, so that's all relational to the sun. That's all proportional to the distance of the sun, the speed in relation to the sun. And we can't, while we can't say that they're right, to be fair, we can't say that they're wrong, right? Because we can't go substantiate it. They just say everything contracts perfectly in relation to it. And it just, it's just a magical, mystical thing about reality that we must take for granted. Okay, maybe we'll grant you that, even though like I already said earlier, this already doesn't make sense with what Fresnel showed us back in the 1800s. Um, but we'll grant it to you anyways. But okay, well, bonjour. My name is Georges Sagnac, and I'm going to take this interferometer that you guys just used to measure the motion, the orbital motion of the Earth. I'm just going to spin the thing. And then when I spin the thing, I'll know how fast I spun it. And then we'll just see if maybe that proportional velocity gets measured in the interferometer. Oh, whoa, what the velocity is measured. Like, whoa, holy cow, man. Like, sorry, and I am French, so don't take offense. I know I don't sound it, but in any case, that direct proportional velocity was measured when he rotated that interferometer. So, just from my personal layman point of view, right? Like I'm looking at that and I'm just thinking like, man, like, well, that looks pretty direct, right? Like that's a proportional velocity that was measured using the speed of light. So that would kind of mean that if the Earth is in a orbital motion, that's just the edge of a rotation, especially when you look at a picture of the circle, the elliptical of the Earth, it looks almost like a circle. And that motion is obviously a rotational motion, and that would be the same thing that you would see with uh with that little interferometer. He spun it and he saw that proportional velocity get measured. He measured velocity in an orbital or in a rotational path using the speed of light. That's what George S. Saniac did. And that was in 1912 or 1913, I think was when it got published. But and he did a bunch of experiments with the speed of light. But in any case, in 1916, uh, Albert Einstein came along and published another paper. So we have special relativity, which had laid out this constancy of the speed of light to explain why they can't measure anything with it. They can't measure any motion with it. And then George S. Saniac's like, well, turns out you can. They're like, oh, shoot. Well, 1916, Albert Einstein puts out general relativity. And he says, well, although an orbit looks kind of like a circle, in the paper, he says the phrase curvilinear. And I looked it up. Apparently it is a word, but I had never heard it before that. And what it means is that it looks like it's curving, but it can only be measured as linear. And you would only feel it as linear. It would only ever appear linear. And it's all because of the bending and warping of space-time. And so it's space-time is warping, and we are on a geodesic that pulls us on this orbital path around the sun. But we only perceive it to be linear. So, oh man, okay, I'm having a hard time, but we'll grant it to you, I guess. Because we'll do the thought experiment. So that's the second time, right? Okay, so we've got or so yeah, so we already debunked special relativity twice, and then now they brought in general relativity. Oh boy, okay. So uh this is a bit of like a tangent here, but we'll real quick, we'll go over Dayton Miller because this is all hmm. There's like three different narratives in here, right? Like we've got this whole thing about how uh they tried to measure the orbital velocity, the path, that big motion around the sun, and that was using the Michelson-Morley interferometer, and they didn't measure that. But then uh, they found out. Then George S. Saniac did his thing. So there's the whole thing of like, what are they really measuring? Because in 1925 they came along and they said they've measured the same thing again, essentially, because it was essentially another orthogonal interferometer, and they said that time they measured the Earth rotation. So they now claim the same thing that they tried to use to measure the orbital motion of the Earth. They claim that to be a measurement of Earth rotation. They did it that one time back then. Now they use what's called LIGO, the Laser Interferometer Gravitational Observatory, is their cutting edge version of interferometry. But in any case, that's skipping way ahead, obviously. Uh, but back then they took that one measurement and they said, okay, there you go, Earth rotation. Boom, we caught some motion. We can do some math, scale that out proportionally. Yeah, sure, we can fit that into the Earth rotation. But then Dayton Miller is another guy that before they took that one single measurement, had already started taking a bunch of measurements. And what he did was a little different. He didn't just do a one and done. He took measurements throughout the year. And so he's taking measurements, and he's watching this Earth rotation, quote unquote, that they're measuring with interferometry get faster and slower. It's all, remember, it's just the speed of light. So it's the fact that light is propagating. Like light doesn't really have a speed, right? It's just an induction that occurs within the background medium. But uh but that rate at which it propagates east to west, west to east, that's what's changing throughout the year. And it pulses. What Dayton Miller found is that it essentially pulses with the equinoxes. So as the sun's moving back and forth across the sky from north to south, there's a fluctuation in the ether flow, is what we call it, because it is essentially, you could, through all the measurements that we've seen, it can be so easily explained and conceptualized as a flow of the background medium that light propagates in and that everything exists within. That's just a simple, concise explanation that we can absorb the first order measurements. Or some people will argue that you can't have a first order measurement of the speed of light and the second order, blah 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 blah. I would argue that in 2004 it was generalized by Ruyang Wang, and so especially when you look at what he did with the phase conjugate mirror, you can call it a first order measure. Anyways, I digress. I Let me slow down. So the point being here that I the Earth's not spinning faster and slower throughout the year. That doesn't fit with their model. That's silly, and that's why they all just they there has been multiple papers now where they won't let us see Dayton Miller's actual readings that he took. We don't have those, unfortunately. All we have is the analyses that were written about him back in the day, saying like, "Wow, if this is true, then that Einstein's works." Einstein himself said if Miller's works is true, then the relativity collapses like a house of cards. So they all knew that if this was all real, you know, then something's up that doesn't fit with their narrative whatsoever. Um, so that was Dayton Miller. He started that in the 1900s. He did it. Um, he took a ton of measurements in the early 1900s in Cleveland, and then he found those. He started to get an inkling for what was going on. He started to learn about how the interferometer works. They're super not fragile, but what's the word I want? Just very easy to disturb. Like, it can, like, vibrations outside, temperature fluctuations, pressure variations, all these things can give.
Sensitive.
Very sensitive, yes, highly, highly, highly sensitive, and, so he was learning all that back in the early 1900s in Cleveland. He did, uh, tons of measurements. He, perfected the interferometer, added mirrors to it, started learning about it, and then in the 1920s, he went to, California, and he went up to a observatory, the Mount Wilson Observatory, which was at a much higher altitude, and when he started taking measurements there, he found that the ether wind flow was a greater velocity. There was a higher reading of that measurement of what they would have called it Earth rotation. They tried to measure it as orbital motion. So um, that actually fit with what Georgia Sanyak had been saying, by the way. If you go and look, Georgia Sanyak will claim just as much and apparently did some of his own tests of the same. Although to be fair, I have not found that primary source of when he did that. But so it was corroborating what Georgia Sanyak had hypothesized or said about the fluctuation at altitude, and he found it was a pretty much greater velocity. It's like 3 kilometers per second. Depends on, how you look at the fringes, but it's like 3 kilometers per second in, Ohio, and then it was like 9 kilometers to 11 kilometers per second. Of course, it depends on time and year too, uh, in, uh, at the Mount Wilson Observatory in California. So, when you're at a higher altitude, you're getting a higher reading, especially with the ratio you look at, even if you were going to allow them to call it a linear motion or a linear vector, you would never get that ratio of change. And so it totally doesn't fit within their model whatsoever. Uh, and so that's why they don't talk about Dayton Miller. And so the other thing Dayton Miller did was he realized that these readings were sensitive to the air, right? They were sensitive to, like, basically, if you shielded them with metal, it was not, you were essentially nullifying the reading, right? And that's kind of what they do now is they try to nullify the reading. They put them underground. They put metal shielding around them so that they can, get a null result because they expect the null result. That's what relativity predicts. And so they do everything they can to basically block out the ether flow. And so Dayton Miller had he had written explicitly about the fact that he thought that that the metals that they were using in these interferometers were causing problems, and no one ever acknowledged it essentially. Uh, and so yeah, that was the 1920s. 1925, they did their measurement. They said that they measured the Earth rotation. Uh, and then we go through history a bit. What should we let's see here. So GPS starts to become a thing sometime around like 1990s. They're really starting to work out the details of like they're trying to get GPS to be like super precise, and they're trying to work out the details of range measurement that GPS uses. And so, some of the more free thinking minds are looking at it, and they're not trying to force it all into a relativistic framework. Or maybe it was just some of the more brilliant minds of the time. I'm talking about people like Ron Hatch and Ruyang Wong, uh, and what's his name? GPS and the constant velocity of light. Paul Marmé. People are looking at it and they're saying like, "Hey, like, uh, this debunks special relativity. The way that these GPS crafts work, and the way that they have to rely on the velocity of the craft, and they have to take that into account to figure out where they are, and in order to keep their atomic clocks in sync, like that means that special relativity was wrong." So here we go, another time special relativity is wrong. I so people are starting to write that and they're saying like, "Hey, like this looks like classical mechanics," which is funny because they'll tell you that there's time dilation in these things, right? That's like a kind of a separate part of this. There's two parts of the GPS thing that are both very important to the discussion. And the first one is that it's the way that they work, the range measurement that they use relies explicitly on the speed of light being proportional, or the speed of light not being constant, because I have to take in the proportional velocity of the receiver craft, which is not supposed to happen. Everything's speed of light is supposed to be the same everywhere. It's never supposed to get faster or slower depending on if you're moving towards it or from it or whatever. So there's that, and then there's the fact that they'll tell you that GPS crafts, GPS satellites are proof of time dilation, and that it's this crazy thing that happens with just the bending and warping of or just the dilation of time. Time is just fitting into what has to happen in order to make these clocks go away. Well, like it couldn't possibly be related to a mechanical process with the or a classical process with the electromagnetic or the electromagnetic field that's generated within the atomic clock. And if I don't know if we're gonna go super deep into atomic clocks today. We may. Alan started going through a presentation about it yesterday. We've done numerous presentations about it before, but there is an electromagnetic component of the atomic clock. That's the important part to understand. And that electromagnetic component retards directly proportional to the movement of that
Oh,
craft. What's up?
yo, yeah. So the electromagnetic retardation within the clock. That's what you're. I think
Yes.
that's what you're trying to say.
Yeah, did I say sorry,
Yeah, I think
that
you said
yeah,
it weird.
okay.
You
Yeah,
said
so
it. You said the magnetic field in the clock. That's not
the electromagnetic
retardation. That's going like
retardation. Well, the
yeah.
retardation of the electromagnetic field, right?
No, of the electromagnetic propagation that's going on inside of it. So you know how they use the radio waves that they
Mm.
ionize with the
Yes, for
gas to
waves.
get
Okay, yes, yeah, it'd be
yeah.
propagation. Okay, yeah,
Yep.
yeah,
So
gotcha.
that retards proportional to the velocity and requires additional energy input so that they could maintain that oscillation rate for that conversion of 9,192,000,000 oscillations per second.
So there you go. But the point being that it's not time it's not anything, time's not changing. The clock is losing time because of the way that it works and the velocities that the GPS crafts are moving at. So that's always fun to, be told that time's changing, and then you go and look and it's like, well, no, this actually just has a classical explanation. But then also, like I said, so now you've got these guys that are looking at this and they're figuring out that, maybe, things had kind of been pushed under the rug for however long, or, or maybe just people had given up on trying to disprove special relativity because of the institutions making it too hard to do or something. I don't know, but GPS started to make it clear to a lot more people that something's going on. It's not, special relativity is not so straightforward. And so Ruyang Wong, one of these people that wrote about it and collaborated with Ron Hatch, who exposed it, I think, pretty well in his book Escape from Einstein. Uh, Ruyang Wong decided, well, let's just like put this to rest, because we're not supposed to be able to measure motion with the speed of light, quote unquote, at least not linear motion. They say it's okay when it's rotating, and that's why we can't measure that orbital motion but they say, because it's actually linear, it's curvilinear. So let's test it. What I'm seeing in GPS makes me think they're wrong. So let's test it with locally. And actually, I did skip over something very important. So I'm going to digress real quick here. I So I brought up earlier that they talk about proportionality to the sun, relationship to the sun, and then he rotated his little interferometer. George S. Saniak did, and he saw. I don't know why I call it little, but he rotated his interferometer and he saw that proportional velocity get measured. And uh, although they say, like that's just because it's in a closed loop, there were still like they still have to have a physical explanation of it, right? Um, and so the papers they write to explain that. Um, who wrote? What's the? Can't think of the author's name, but there would be a paper. I think it was in the '60s. It was written. Um, And what they end up doing is, you remember the crazy looking chart that we showed earlier, showing the bending and warping, or the time velocity chart. They do the same thing with that little with the interferometer. So it's in front of his face. It's on the it's in the lab. It's in the or it's in the science lab, and he's just rotating the device. So you don't have the same like, oh well, we don't know for sure because we can't really test because we don't know in relation to the sun. Like, maybe we can't, even though we can't prove it, we can't disprove it. Well, it's like with this, when it happened locally right there, it's like, well, geez, like, I mean, literally what's being measured, like the measurement is there. It's a fringe shift. And so the measurement is taken at the like it's a physical measurement. It's something you observe with like what someone observes with their eyes, right? Like, or someone that you could observe with you could capture that moment in time. You could capture a photo of it or whatever. It's an observed event. And so although they can do the math, they can do that Lorentz transformation, the observed event is still perfectly explained by classical mechanics and only explained by classical mechanics. So even if you want to grant them their curvilinear path, just remember that you can only explain the interferometer rotation with classical mechanics, and you can't actually predict it with special relativity. And so you fast forward now to 2004, this Ruyong Wang guy that's been looking at GPS, he's going to do the same thing to them again. He's going to take an interferometer, he's going to introduce a linear portion. They take fiber optic cable, or he takes fiber optic cable, him and his crew, and they hooked it up to a fiber optic gyro, and essentially they move the whole cable, and there's linear portions of cable. I'm sorry, I'll pause for questions in just a second here. There's linear portions of cable that move with it, with the conveyors, and there's three. The first experiment had three linear motions that were occurred or that were in it, and then the second experiment had one linear motion that was in it. It's kind of hard to explain without visuals. I guess I could throw it up in the jumbo. But the important point is, he kneecapped them again because it's like, okay, you guys measured the local rotation. You had to explain that with a Lorentz transformation. Now we do the same thing with linear motion. I did it locally in my lab. It's not in relation to the sun. It's not in relation to something in outer space, but I went there and I looked and I was able to measure linear motion with the speed of light. He did that first in 2003 with he borrowed a fiber optic gyroscope, a very high fidelity fiber optic gyroscope from the Naval Research Laboratory, loaned it to him, and then he did it. He immediately filed for a preliminary patent on that exact concept, and then he did it again. He got another loan of a fiber optic gyro from the Naval Research Laboratory again in 2004, and then he wrote about in 2006. He did another experiment to talk with a phase conjugate mirror that I'll get into in a second. But also, just really quick, he's not the only one nowadays with this patent. Since then, there's now, if you go look in Japanese patents, Nikon and it's Nikon and who is it? Toyota. There's two Japanese companies that have a patent on this now. So make of that what you will. Some people try to call Ruyong Wang's experiment unremarkable or something, but I don't know why there's so many patents that why people would want meaningless patents. Uh, so anyways, so They did the same thing with that. If you go and look at the explanations from mainstream science about what Ruyang Wang did in 2004, either they won't look at his work and they will just try to discredit him for because he wasn't from enough of a mainstream source, even though like the Naval Research Laboratory was interested, but they're not in, these people aren't interested, in the experimentation that he did. Uh, they'll either try to do that or, at least they do have a mathematical explanation. They can do the math. I don't know if that impresses anybody. It doesn't impress me. I could give you math for, we could give you math for a lot of things. Actually, you give us enough computational power, we can give you like math for almost anything, right? Like especially, the further we go into this crazy computational world. But in any case, um, it's not predictive. That's the other thing that's really important, right? So Ryong Wang showed that that proportional velocity was directly, it's like the speed of that fiber optic cable gets measured in the fringe shift, or so the measurement of light, that speed of light gets measured proportional with that linear velocity. What that means is that we should be able to measure the motion of the Earth using the speed of light. So let me pause for questions or if anyone else wants to get in.
I can understand from a relativistic effect why you wouldn't want to acknowledge Wong's linear measurements, but what's the apologetics for not being able to measure a linear measurement with interferometry?
Uh, well, I mean, we
I got
can.
you with the with an orthogonal setup. So with that cross setup from Michelson-Morley, for example, you saw how the mirrors make like finite points, and there's not that many of them, right? So there's a different sensitivity threshold for measuring motion with them. So when you have the closed loop circuit, you you effectively have infinitesimal points of where you can measure, where you can be aligned with that motion. So when they wrap a coil, for example, uh, they're creating multiple infinitesimal points. So it's just a sensitivity thing. Like you absolutely can. It's just with an orthogonal setup, there will be a difference in the measurement, but it'll still be there. You just won't be able to measure it, because it's also, you got to understand too, the Michelson-Morley experiment was like the way that they had the light reflected. The distance of that was like 76 meters. So it's like they're taking a length of 76 meters to try and get a measurement, and it's only going to be sensitive to certain points, right? So the closed loop is definitely the difference maker in that regard, and that's why. And then how you could stack it, or like coil the loop on top of it, like that just creates multiple points. So it just makes it more measure it more better or whatever. I'm pretty sure that's a science word. Sorry, you can go ahead and continue, or you can continue, Toby.
Cool. Yeah. So, do we have any speaker requests, or I'd like to get Shane up.
I tried to give out mics, and I tried to rotate mics, and nobody accepted, and it didn't work, and it didn't remove the people that I rotated. So I don't know.
All right, I'm gonna go check on that really quick.
Yeah, give us 1 second. We'll while Toby's doing that, we'll touch back on GPS for a second. So I put some stuff in the Jumbotron, and we'll go over the pictures from left to right here. So Toby was touching on engineers that over the years were working in GPS. We're like, hey man, where are those relativity corrections at, right? Because at the time there was what was they doing? Like, so like the government, these different agencies that work in GPS and whatnot, were like, hey man, we need to make it more accurate, more better. And they're like, how do we get more better? what equations do we use? And they're like, we don't know, but just do it and we'll get around to it, right? So that was 1 second. The screen just turned a different color. Is everything still working? You guys can still hear me?
Yeah, give me co-host back. You have to just rejoin Twitter every now and then for everything forever.
Oh, okay. Yeah, okay, so 1 second. Let me back to the picture. Sorry about that. Okay, so anyway, all these engineers and DoD workers and whatnot were like, hey man, how do we make it more accurate? So, what is it you want us to do here? Because we're not even including relativity in it. And you're telling us to, put these models in, and none of this works. So they say here that, look, guys, this is basically like the overall summary, but you can definitely read it. Highly recommend. But what they say here is that the equipment that they're using, right, isn't sensitive enough to account for general and special relativity. So what we kind of didn't really touch on is during the course of, so 1905 was the acceptance of special relativity, where they said we can't measure linear motion, we can only measure angular rotation, right? So they said that the orthogonal setup and the ability to measure linear motion wasn't possible. Now they didn't go with the ether contraction mechanism, right? They said no ether, but space and time distort in proportion to the velocity. So same mathematic mechanism, but just different words coming out of your mouth to explain it. And then for general relativity in 1915, they were like, okay, there's gravitational fields and those also distort space-time. So now not only does mass distort space-time, but not only does velocity distort space-time, because special theory is a theory on velocity, right, and how that distorts space-time. And then the general theory is about gravitational fields and how that warps space-time proportionally. They use the equivalence principle to link the two theories, right? So they say that if you're in a gravitational field, your time's going to dilate, your length's going to contract, all that kind of stuff, and you're not going to be able to experience, or you're not going to be able to tell, or whatever, right? And they say that when you're moving at a fast velocity in linear motion, you're not going to be able to tell, right? So like same equivalence. That's how they get it all in there together, right? Now for GPS, they're saying, hey, the Earth, it's a body in space or whatever, so it's got the old gravitational field. So we're going to need to introduce general relativity corrections to account for that gravitational field. And for the special theory, well, first of all, we're going to need to account for the principle of relative simultaneity, which we haven't got to yet. But the velocity and time dilation, right? So the velocity component, like the speed in which the crafts are traveling, is going to produce a temporal time displacement relative to an observer on Earth, right? So that must be accounted for, all these things, right? So we saw that there was a specific equation used earlier, the Lorentz transformation, right? We saw how they do velocity addition relativistically, right? There's a certain gamma factor correction involved that gives you that relationship, so you can dilate the time and link and contract the length and all that. So these guys were not doing any relativistic math. They said that the special and general theories canceled out. Basically, how fast the satellites were traveling at the altitude they were traveling canceled out the gravitational potential corrections that would be needed, right? So Toby was saying earlier how the clocks inside how the atomic clocks inside the satellites retard proportional to velocity, meaning if you have, so they keep time with 192 million oscillations per second, right? So if you think about a spacecraft moving at, it could be any craft, it doesn't, whatever a satellite is, just assume a velocity of 10,000 kilometers a second. If you took that and applied that to the oscillation rate that the atomic clock is supposed to be experiencing, instead of oscillating at 9,992,000,000, it's oscillating at 9,182,000,000, right? So it lost 10K oscillations per second, right? And that's not supposed to happen. Now, they're saying that their equipment that they had at the time, that reduction due to the gravitational field and the velocity of the craft to account for time dilation wasn't enough, that they canceled each other out, right? And it just was a null effect. So they could just use classical mechanics to explain this. And then on the next picture, it's just more of them going through that and explaining how, or what I just explained about the acceleration and the gravitational field canceling out and their equipment not being sensitive enough, et cetera, and that they definitely account for them, but they cancel out. So like, don't worry about it, guys. Now, when they got more sensitive, now we'll look at the last slide here where it says GG at the top. This is at the end of this paper. This is from Carol Alley, who writes in, on these technical manuals and these meetings and is trying to figure out what's going on with relativity and GPS. He says, and that if one perhaps does the explicit recognition of special relativistic effects, I mean, it took a long time to get general relativity down properly, but I think it's more or less correct now. But its absence of any explicit acknowledgement of special relativistic effects due to the speed of light being the same whenever measured by an observer leading to the relativity of simultaneity and the associated Lorentz transformation physics. There is nothing of that modeled in the current system, and I think it should be. Thank you. So what this man's just laid out, you know how we're all told, oh, relativity proves GPS, GPS relativity, GPS relativity, Einstein, atomic clock, all these things, right? All these buzzwords or whatever, right? The principle of relative simultaneity says that because there's no absolute space, like, unless you're in rotational motion, of course, right? There's dude, how crazy is this? There's an absolute space for rotational motion to be measured against, right? So you can do that. But for linear motion, there's no absolute space for that one. Sorry. So it's just different. It doesn't work that way. Even though if you extend a rotational vector out to infinity, it would be linear. Like, there's no, sorry. So anyway, this principle of relative simultaneity is the justification for length dilation and time contraction, length contraction and time dilation. So what this means is, if there are observers in relative motion to one another, they will view events differently, right? So we've all heard the example of the moving train car with an observer in the center and a stationary observer on a platform. And as the train's going by, when they intersect and lightning strikes, the moving observer sees one of the lights flash flash first, and then the stationary observer sees them flash both, right? There's not a cohesive timeline between them. And if you were to add more observers and more velocities involved in that, you would get a cascading effect of people experiencing things slightly different from one another, right? And this is what they've put forward. Now, obviously, the speeds involved would be faster for those effects to take place, for the observers to notice them themselves. But luckily, we have GPS propagation signals, and we could test the train lightning thing, right? With how GPS works, because GPS is a time interval system that makes its measurements based off by sending a signal at a specific time, and it sends the time that it sends the signal, and then when the signal is received, that difference is multiplied by the speed of light, and that gives them the distance that had to be propagated. Now, sometimes it's plus c, sometimes it's minus c, and what happens, what they find is that observers that get the same signal all sync to a cohesive timeline with no problem, right? So this would be functionally impossible if relativity were true and they try to make a GPS system. You absolutely could not have GPS working in 1995 and have it sync to a cohesive timeline and not use Lorentz transformations. You would have to account for the cascading time dilation. You would have to do something, right? The atomic clocks on the crafts themselves relative to one another would be experiencing experiencing effects that would need to be corrected for. They're making none. This is the fundamental backbone of the whole theory. So let me break this down again. So earlier we were talking about the sun and the earth and the motion there. So this apparatus that they were using to measure that velocity is supposed to contract by a certain amount in our reference frame, right? In the earth, in the lab where we're measuring it, right? Due to the velocity we're experiencing. But suppose there's somebody who's traveling, next to the earth, but they're at 28 kilometers a second, right? They're going to measure a completely different amount in our frame, they're going to see a completely different amount of contraction, right? It's not going to be that same amount proportional. And that's in reference to that there's no cohesive timeline. So nobody sees the same thing that we're measuring, right? Everyone will be different. Now, what GPS proves is that everyone measures the same thing. Dude, regardless of their velocity, they all get the same signal. It's all on the same timeline, and it all works out. Any questions, comments on that? Because that's hugely important, because this undermines everything. And the fact that engineer wrote like that and was like, hey, Mr. Guy in charge of GPS open source program that verifies relativity theory and the correctness of it, how come there's no relativity corrections in here, right? Blah, blah, blah. And how come we don't account for the principle of relative simultaneity? How come we can just have a cohesive timeline of events and people at different velocities having the same measurements? How can it all be? How can it all work like that if relativity is true?
Not to mention the syncing of the clocks within them that have to be in a classical Galilean coordinate system in the first place before they do their arbitrary corrections.
Well, it's funny you mentioned that because you're 100% right. That's what the proportional velocity correction is on the atomic clock, and that's explicitly not supposed to happen. So while they were trial and error setting up this system, so GPS atomic clock synchronization, by the way, GPS time is one of the most fascinating and intricate things in the world. It's maintained with constant corrections to it 24/7. There's like a full-time, staff for it. It's crazy. It's like the most significant thing that they work on, like keeping this time. And because of how sensitive the devices are, because of how of these corrections and stuff, everything has to be, they can't. There's no wiggle room, right? So what we have is that was in 1995, right? They're like, hey, relativity is coming, guys, look out, right? So in 2000, we have Paul Marmay's paper where he goes over the general relativity corrections that they put forward as proof of general relativity, and they have their gravitational uh, potential correction that they finally added. They have a time dilation correction that they finally added, and all of that, right? Now, what he breaks down in the paper is that the equations that they use are actually the same equations that you would use to make Sagnac corrections. Now, if we remember back to earlier, the Sagnac effect is, one second, I'll pull up the equation for it so we can go over it together. The fact that GPS accounts for this and they say it's a different type of thing. No, this is a temporal thing. Nope. Nah, absolutely not. It's because it's not even there's not even Lorentz transforming. One second, trying to remember which. Oh, it's in this one. Sorry. Pull up the equation here. All right, it's coming right now. All right. So in the Jumbotron, one second. Does this work? Yeah. Okay, so in the jumbo here, we have the Sagnac effect linearized. Now you can ignore the linearization part for now, but just look at the equation. We have the delta t, so the amount of fringe displacement is going to be equal to 4 omega a over c lambda, right? So this is just the angular speed. So this is just velocity, and then this is length. This is just the area that light had to travel in the apparatus. And then this is over the speed of light times lambda. And what that gives you, right? All the important thing to note from that. Sorry, I lost my train of thought, but then I instantly remembered. So we're all in luck. So what the important thing to note here is that this is a velocity correction, right? This is a velocity ratio to the speed of light. This isn't this isn't a gravity thing or anything like that, right? What these equations represent. Now, what Paul Marmay pointed out in his paper is that the equations that they use to account for general relativity effects. So they say that the satellite is at that the GPS constellation of satellites is at a specific altitude, and they say that altitude there's a equigravitational potential there. They have to make like a fixed correction there. It doesn't deviate. It's not like fluctuating or whatever. And the equation that they give is identical to the Sagnac effect, identical to correcting for this, correcting for velocity over the speed of light. And then they say that the time dilation equation that they use to account for, oh, sorry, it's not time dilation. They say that they have a velocity correction for Earth rotation, right? So if there's a velocity correction for Earth rotation, well, that's also the Sagnac equation they use for that. And the one that they use to, let's see, what was the other one? Velocity, and then okay, so then they do another, dude, and then they do another SAGNet correction, they call it, but they don't do it as a velocity correction. So in this regard here, they don't do, it's not like a ratio against the speed of light versus over the velocity or anything, right? What they actually do is they do a coordinate system transformation. So earlier, how we were saying how the x-axis is your direction of motion, and then your y-axis is always perpendicular to that. So if you think about an xy graph, the time axis would always be where the y is at. And let's see, lost my train of thought there. Sorry about that.
But you got it back instantly?
No, not that time. Not that time, unfortunately. Not that time, unfortunately.
Yeah, you did last time.
Yeah. So let's see. They got their time divergence graph, but the bottom line is they don't use anything like, oh yeah, I'm sorry, I remember now. The transform. So instead of making a velocity correction like that, like previously, right? Like an oscillation correction to the oscillation rate, right? What this is they're inverting the y-axis and the x-axis. And if they don't do that, they'll be off by 30 meters. So that's the final correction they make. And I have it on record from a paper by A.G. Kelly where he emails the people that are in charge of international clock synchronization standards and GPS standards. And he's like, hey guys, what's up with this SAGNet correction? Because like we got these corrections, right? These look like velocity corrections. These look like corrections you would make, right? And then we got this coordinate system rotation that you're calling a SAGNet correction. This isn't a velocity correction. What is this? And they write back and they go, you're correct in stating that it's not a relativistic correction. And that's all the detail they provide, really. So I'll put that up in the jumbo if you want to take over, Toby, and talk now for a minute about the next subject.
Yeah. Yeah, I think I totally, we haven't even gotten into Galev yet, so I think I'll just kind of take us there now. Unless anyone has any questions, I did not see any other requests for speaker, which is all good. You don't feel obligated to come up and speak unless you have something to say or ask. But yeah, so I just moving along. We talked about, I briefly went over Dayton Miller. Alan touched on Dayton Miller, and about how he was measuring that periodicity, which by that I just mean the fact that 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 preferred direction of the speed of light, the fact that it goes faster one way or the other, quote unquote speed of light, the fact that that happens and it changes throughout the year, I call that the periodicity, right? That would be the term for that, because it's the fact that it has a periodic effect, and that there's the period changes of or it matches the period of the motion of the sun in the sky, essentially. And so now, if you think about it, if you really just look at it from a logical framework, if the speed of light is fluctuating with the motion of the sky, the directionality of the sky. Now, they would argue it's the directionality of the Earth, but I would, we're trying to make an assertion about relative motion, right? The weird thing about, if you try to say it's the rotation of the Earth, is the fact that it matches the motion of the sun. And also, I touched on how if you go up higher at altitude, you shouldn't get such a drastic change in your reading. But so when you try to conceptualize that, the measurement of motion that you're taking is matching the position of the sun in the sky. So this, in their model, would have to be the orbit, or not the orbit, sorry, the rotation of the Earth. But the rotation of the Earth, the speed of that shouldn't change, 30%, more than 30% based on where the sun is in the sky. Now if you look at their math, if you look at their model, they do have some fluctuations in rotation speed, and that's a whole nother topic. that are or that are measured on their elliptical that are kind of inconsistent as well. But that's not consistent with what we're discussing here. That not at all. The Earth doesn't spin faster in their model by 30% ever. That's not how that works. So there's that component of this that was measured by that Dayton Miller guy. And he also measured that difference at altitude. Both of those things are very hard to conceptualize within a Earth going around the sun model. Very hard to conceptualize because you have to somehow they do calculations. They have to abstract out these ideas of how those motions in the sky would be translated directly like that because it should be relative to um sorry, I'm getting a little in the weeds here. I let's just What's the best way to put this? The point is it's a first order measurement, which I got into already. I'm being a bit redundant, but it's a direct measurement. And so when you see that direct measure and you don't get the velocity component that you expect, you don't get the speed that you expect, um, and you try to call it rotation, they try to call it rotation, like none of this is adding up. And so you think, well, maybe that Dayton Miller guy was wrong. Well, in Ukraine in 2001, there was a man named Yuri Galev who did more experimentation. He used radio wave signals and transceivers. And now a radio wave is still an electromagnetic wave, and light is an electromagnetic wave, all in Einstein's framework and in classical mechanic framework. Now, in Einstein's framework, it's also a particle, but that's not the point here. Uh, it's still so the radio wave is still it's supposed to obey the same rules of special relativity that a light wave takes. So the fact that he's using a radio wave, you can just think of it, it's for all intents and purposes, it's still c, the velocity of light, quote unquote. It's supposed to propagate at a constant speed, and it uh, follows the same rules of that periodicity that I was talking about. So he used radio waves and he sent them at multiple angles from the top of a mountain down to transceivers, and he measured that reception time, the difference in the fluctuations in that reception over the period of or over the course of months and months, which allowed him to then calculate out the same periodicity that Dayton Miller came across. So he reanalyzed all of Miller's results and said, "Yeah, this is what I'm seeing is periodicity. The data that we have not been able to obtain publicly." I I'm gonna do another attempt at that here soon, but I in any case, he corroborated all that, and then he went and he did his own experimentation. He did 2 experiments. So there was the one he did where he's shooting the radio waves down from the mountains, and what he found is that the velocity he did a bunch of proportional relationships. He looked at the way that essentially that these different radio waves, the the propagation rates that they were happening at, depending on the angle he was shooting them at, allowed him to deduce essentially the difference in the velocity gradient. So like as you're going higher, he was able to tell which altitude or which part of the gradient at altitude was having how much of an effect on the light essentially. So he's able to deduce that the the speed of light, that preferred directionality was higher at altitude. Exactly like Dayton Miller found, and it had a periodicity, exactly like Dayton Miller found, and it matched with Dayton Miller's findings. So this was experimentation that was pretty explicit about matching Dayton Miller's findings. And then he did more experimentation. Remember when I said that Dayton Miller said that everyone was putting the interferometers underground and putting metal around them? Well, no one really ever quantified whether that was necessary or not, or what kind of how that played into these measurements. It was never put to the test through experimentation, science. And so Yuri Galev put it to the test via experimentation. He took metal shielding, he put it around one of the arms of the interferometer, and then he shot fluid gas across it, and he rotated the interferometer so he could use essentially it was Bezellian functions and it was essentially fluid dynamics math to derive using looking at the differential between the laminar and turbulent flows and how that would be related to the rotation of the interferometer through the flow of the gas. he was able to deduce how much of that flow was going through the or through the metal shielding, and how much of that flow, how much the light was affected by that flow relative to, um, the orientation of that interferometer. And what do you know? He found that that the metal shielding had a very a very strong effect on blocking out the ether flow. And so, and it still does come through in the reading, but which is something to contemplate in itself. But but yeah, so that was uh that was corroborating Miller yet again, because Miller was pointing out that you guys are putting metal shields over your interferometers every time you're doing these tests, and so you're not getting the same result that I'm getting. And that I was looking for sensitivity. You guys are doing the opposite of that. So you're not going to pick up on the reading when you're trying to cancel out the sensitivity of the reading by seeking a null result consistent with special relativity. Now, let's pause, I guess, real quick for questions if anyone has any thoughts or questions. Cool. So let's jump ahead to modern day if that's cool. Does that sound good?
Yeah.
Cool. So in 2017, I like to bring this up to kind of put a framework around LIGO, the Laser Interferometer Gravitational Observatory, and all the current readings. When I was digging into this, or part of digging into this, someone brought me a reading from 2017 where they used frequency and resonance cavities to look at electromagnetic wave propagation. And they said, someone sent it to me and said, here you go, proof of the speed of light. And so I thought, oh, or proof of the constancy of the speed of light. And I thought, oh, okay, let's take a look. And so I went and looked at that paper, and they didn't show the direct measurement. They showed that they explained that they used an error weighted least squares regression model to account for seasonal variance and daily fluctuations in seasonal variance of the quote unquote speed of light. Or so that's exactly what Miller measured. That's exactly what Galev verified. And in 2017, they're using statistical analysis, or they're using mathematics to essentially, I mean, yeah, they're using a regression model, or error weighted regression model, to cancel out the parts that would disagree with the predictions of special relativity. So you're not looking at a direct measurement, you're looking at a measurement of what you expected to happen. And I found that very worrying and odd, right? Like, it's like, oh, what do you know? Like, the more I dig into this, someone comes to me with a proof of special relativity, and then I look at the paper and I'm like, it's like, is anyone not looking at this where it says this right here about how they're like literally accounting for this? Um, and so that got me thinking. And then, you start looking into what they do at the Laser Interferometer Gravitational Observatory, and everything that when they say that they measure these gravitational waves. So now what they do, they take this a step further, and they say, not only can we measure the spin of the earth, but what we do now is we say that black holes coalesce in outer space in these things called gravitational waves, or there's cosmological events that happen that cause gravitational waves to propagate, and we pick that up with the Laser Interferometer Gravitational Observatory. And they say that's proof of general relativity of the gravitational waves. But that's another topic. But in any case, they say they picked that up using the interferometer. And the when you look at how they do this, the data that they look at is called noise. The actual measurement is literally a noise signal, it's called. And they take this noise and they run it through what's called a convolutional neural network. And the convolutional neural network is like a super high, like an insane super, like it's a whole network of supercomputers, right? It's a supercomputer network that's doing. So they used to do what was called deep filtering, and now they've taken it to the convolutional neural network. But essentially, there's multiple layers of filtering that all the data goes through, where in which they extrapolate out all the data across multiple. It's called the convolutional part, means that they take it and they're able to extract out the data across multiple dimensions, and they stretch it and compress it across multiple dimensions, and then they go through and they look for signals within that, and then they take those signals and they run classification and correlation on those signals, and then they use the classification and correlations of those signals to then do new pattern matching in the previous layer, and then they're essentially molding the previous layer to fit with something that they want to find, and then they take that and they send to the next layer where they do pooling of all that to where they're allowed to draw correlations between it's all very abstract, but the point is to say that by the time that they get through all of their layers and they do all their classification, they are not looking at anything, in my opinion, meaningful. And the real problem is that it's using machine learning, right? Like they are constantly trying to fit it within their expectations, to the point that I have made the joke that they could find, like, if they gave it enough time and computational power, they could find a gravitational wave in a fart. Like, like it's just it wouldn't be it would just be a matter of giving it enough time and enough computational power, and it's going to keep extrapolating out, finding, increasing its fidelity, reifying itself through uh neural pathways, or whatever, quote unquote neural pathways, which is really just weighted logic, weighted lines of logic. But yeah, so that's where we are now with all this stuff. That's where this has come. That's what they do down there in Virginia or whatever. And those guys, I mean, that's a whole, like, the LIGO thing. We've done a presentation about it. I would definitely recommend checking that out. It's one of our Ether roundtables. It was number 19. We talked a lot about this topic, LIGO, if you're interested in it. But yeah, so that kind of brings us up to now. Does anyone have any questions or any thoughts? Cool.
You
So
can drop me
yeah,
down if you need a speaker spot. Thanks for having me, guys.
no, I think we've got plenty of spots, so all good. But don't feel like you gotta hang out up here either. So yeah, did we want to talk about general relativity at all? You still there, Alan?
Yeah, we can do a little GR because it ties in with Mickelson, Gale, Pearson. I think we could probably wrap it up off of that. What do you think?
That sounds great.
All right, cool. So we'll
Could I ask
touch.
a dumb question real quick?
That
Ab-
sounds awesome as well.
Absolutely.
Yeah, uh, Toby hit on it's taking us back, and I don't want you to spend a lot of time on it, but you mentioned Wong, and you mentioned the patent, but I'm kind of new to all this, and I know the stuff that I know what's attached to that patent, but you didn't really touch on what that patent was for. And I think that's kind of it's a little bit eye-opening because you didn't say what the patent was for, just that he drew a patent. Um, with the standalone speedometer, basically. You can measure velocity with a standalone speedometer, right?
Yes, with the apparatus that Wang patented, that was the idea of it.
Yeah, so you don't need, like on your car, you've got a cable to the tire and it measures the revolutions. But this, didn't you say that he could take one for each axis and you could measure velocity in absolute space?
Yep. Yep. You
Yeah.
could get your actual position in three-dimensional space with it
Yeah,
and
that's
velocity.
that's exactly right. And with a like with an airplane, you have like a really big problem because you're trying to measure relative to the jet stream that you would be in, right? Like you don't know you can't it's they rely on you have to rely on an external frame, like you said. Like with a car, it's the tire, there's a number of rotations of the wheel. And with the airplane, they're going to use multiple things. They're going to use GPS, which is, we don't see what happens under the hood with that. And then if they're going to try and take any sort of proportional relationships to their craft, it's going to be relative to this to the or any sort of speed readings of their airplane. It's going to be relative to the jet stream that they're in. And you can't measure that without getting outside of the airplane and going taking a reading, from stationary Earth. So and you have the same problem on the sea. They have to look at the stars. That's why celestial navigation is so useful on the sea, because they can use the sky to at least determine their directionality. But with like uh but you wouldn't know to try and be specific and like really specific to the level like of knowing your absolute speed and motion on the sea. You're also going to have a hard time because you don't have a good reference frame to use. But what this implies is that you can use the background medium, the substantive medium that electromagnetic waves propagates through, to determine absolute motion via that fluctuation in the quote unquote speed of light. And so, yeah, that would mean that you could take one of these things, if you had one built that was the proper, the proper fidelity, and according to Ruyang Wang, you put it on three axes. You put one up, down, you put one on X, Y, and Z axis, essentially. You could tell your absolute motion through space in every vector. And so that would have massive implications, not just for like precision of instrumentation without any networking, but also for mapping and for determining absolute distances over like things like seas and oceans and continents, things that are not so easy to measure without making assumptions about what's in the sky.
Thanks. I didn't mean to make you go back like that, but to me, that
No, it's a good
seems
point.
really important. Yeah. I appreciate you going over it for me.
Cool.
Being
Yeah, we
able
want to go ahead with.
to being able to know a distance without referencing something in the sky. Wouldn't that be something, Toby?
Hmm.
So we'll go ahead and end on Michelson Gale Pearson here. So in 1925, we're going to see a repeat of the explanation given to explain Airy's failure. So remember how the speed of light has to be the same or whatever, but unless you're rotating, et cetera, et cetera. So the prediction given for general relativity was that there was going to be a displacement in the light that would be proportional to the latitude and speed at that latitude, and it would basically measure Earth rotation. That was what that's what they were prefacing with with Michelson Gale Pearson. So with that, they also had an ether prediction, right? So they once again had a stationary ether prediction, and they were like, okay, so we know that ether, when it's inside of a tube, it carries light in the opposite direction. So the prediction for the stationary ether will be that a stationary ether that somehow moves in tubes, the prediction will be that there's no fringe displacement. So the stationary ether predicts that they won't be able to measure a fringe in the math that they derive for all this, right? This is how they're presenting it to the public. And general relativity predicts that, blah, 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 with respect to absolute, or with the stars, you can measure absolute rotation because with Sagnac, blah, 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 that there will be a fringe shift pattern measured, right? So when we look into the mathematical derivation that they provide, this experiment was actually a little more significant than what's led on, because we touched on earlier with the general theory being linked to the special theory. They're all supposed to be this experiment was supposed to be a test using Earth's inertial mass, right? Because in relativity theory, if you're going to use velocity for something, it's moving fast, so it's going to have a different mass, because in relativity theory, energy and mass are equivalent. When you're traveling really fast, your energy is increasing, so therefore your mass is increasing, right? Like that sort of situation. But if the Earth rotate really slow, then it doesn't have it doesn't have like extra inertial mass or anything like that, right? Or relativistic mass. So they were going to use the Earth's quote unquote rest mass, and they were going to use the framework of general relativity with with an equation that represents curved space-time. So this was supposed to represent like if they were able to derive a fringe shift pattern out of this that corresponds to Earth's rotational velocity relative to the latitude, it would have been meaningful for them in the sense that they could say things like, we could rest mass is covariant with relativistic mass. And covariance is an important concept in mathematics because if your theory shows covariance with known physics, then that's a good thing, right? That means that you're on the right track and you haven't gone full retard. So that's just to put it short. So they could have established a covariant framework right now. The thing with curved spacetime is that what that metric is, they're using the scale of the universe. So they're using like the mass of the known universe, essentially, right? Of all the objects they say in the sky, blah blah blah, that they could bend so that they could have a space-time distortion amount. And then with that distorted amount, they have to establish a rest frame in Earth so that the axis of Earth can be rotating, and then we could have Jesus, it gets so convoluted, dude. So the way it would break down is you would have the Earth in rotation, you would have the Earth's central axis of rotation, right? And that central axis would be with respect to the absolute fixed stars where you could measure rotation with, right? Where it's allowed. But the question becomes with if you're using the curved space-time metric and you have all this gravitational force against you, and how do you determine where the center of Earth would be to make that alignment? And I know that sounds retarded, but mathematically, this was like a huge hurdle for them, and this ruins the illusion of covariance with rest mass, right? Because if you're not covariant with the laws of physics that are derived in the lab frame, then you're just playing around, essentially, right? That's the way they look at it. So for this not to work out with the curved space-time metric would be detrimental. So a guy named Ludwig Silberstein did the general relativity predictions for this. Einstein didn't even try and touch this, right? Other people did this for him. So Silberstein comes in, he tries to do it with the space-time metric, and in his paper, and I'll have it all posted in the timeline when we wrap up here. I'm just trying to get through it. But what he says in the paper, he's like, okay, we're going to have to swap to the flat space-time metric because I can't determine where to place the Earth's center axis to be with respect to the absolute stars with all this additional influence, like whatever that's supposed to mean, right? So with that said, he had to use a different metric, right? He had to use the flat one, which is the special relative, which is like associated with the special relativity metric. So where they're not accounting for the equivalence between gravitational field and mass and all that. This was a huge failure for them. So they do their derivation, they get their prediction. There's a friendship pattern, and they go, okay, so the Earth must be rotating at 15 degrees per hour. Now, we're also in the same predicament here as we were earlier with the measurement with Bradley, right? Where he ratioed the angle of displacement against the speed of light, or against the velocity of Earth against the speed of light, and found that was 30 kilometers a second. So here we have an angular displacement amount that when you plot it against sidereal time, it shows a match which would correspond to 15 degrees per hour of rotation to produce what was measured in Michelson-Gale-Pearson. But how do we determine if it's Earth rotation or if the Earth is stationary and there's an ether drift? Well, good evidence for that would be if the attenuation of the drift, right? So in relativity theory, when you increase in altitude, when you move away from the Earth, the 15 degree per hour measurement relative to that latitude can't change because you're making a measurement with respect to absolute space according to them how the device works, right? What that means is, so think about like a rotating sphere, and then a line intersecting the center of it, like a hypothetical line of any thickness, infinitesimally small, even, right? It's the smallest thing you could imagine intersecting that. That's rotating at 15 degrees per hour. That's causing the overall sphere to rotate at 15 degrees per hour. The measurement you're taking with the gyro isn't measuring the surface rotation of the Earth or anything like that. It's measuring with respect to that infinitesimal finite point at the central axis, right? That's what they're claiming. That's why they say you have to align single axis gyros to a specific angle, blah, 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 right? Now, let's see here. Where were we at? Angles, measurement. Right. Okay. So back to determining which is what's producing the motion, right? So we know what they're measuring. We know that if we increase in altitude, there can't be any attenuation, right? It can't increase or it can't decrease like the amount that it reads. Now, what we laid out earlier with Miller and Yuri Galev is they measured a vertical velocity gradient that increases with altitude. So when you increase in altitude, that angular displacement that they're measuring would increase, right? They would get more than 15 degrees per hour, right? And then if you do the translational speed on that, it would be it would be the velocities that Miller and Galev produced, right? And how, like Toby was saying, those fluctuations or those measurements have a periodicity in them, where the Earth would be fluctuating, thousands of miles per hour daily, right, and annually, like with even more extreme fluctuations on the equinoxes. So this is direct evidence against the measurement being proof of Earth rotation, because what this means is that the source of the rotation of what's being measured, like what produces that 15 degree per hour measurement on the surface, isn't due to the Earth rotating. If it increases at altitude, that means the source of the rotation isn't a rotation with respect to absolute space at the central axis of the Earth, right? It means that there's a causal mechanism of that, right? What Toby laid out earlier with Yuri Galev and the hydrodynamics of how light works, right? If the source of the motion is the sky, then the translational speed is going to increase as you get closer to it. And that's exactly what the readings show and reflect. So you can combat, these measurements, right? But you would have to do it. The only viable explanation I've found is through like an ether wind mechanism, through light responding hydrodynamically in these experiments, right? So earlier we talked about how they were looking for a displacement every 3 months or whatever. They would take measurements, and like those 3 months would line up with the equinoxes, right? That's what Miller did. That's what they measured, right? But they never got the velocity that they needed. And they can't have a periodicity of thousands of miles per hour if they're trying to say that you can't measure linear motion, only angular displacement. I mean, only angular velocity, sorry. So that it completely contradicts the model. That's why they ignore all these measurements and deny it, because it's a direct refutation. It shows that the cause of the measurement isn't due to Earth moving, because Earth has to move at a specific speed, and they could definitely measure, like that. No one disputes that you could measure angular rotation with a gyro, right? It's the same concept with a linear, measuring it linearly. They've just told everyone that you can't do that. And it wasn't until 2004 that we found out you can, and through GPS, obviously, right? Because the signal propagation is proportional to the observer's velocity, irrespective of whether or not it's rotational or translational. No matter. It's still going to derive the correct distance proportional to your velocity. And the only way it could do that is if there's a medium through which the waves are propagating through which all motion is relative to. Right? This similar situation, a similar way to think about it would be sonar waves and sound. All right. I think that's everything I wanted to touch on for Michelson, Gale, Pearson. They strawmanned a stationary ether position so that they could make it appear that the only viable explanation was that there's Earth rotation. Right? Because the thing with kinematics and dynamics, man, just introducing another velocity component completely refutes the idea that the Earth is the causal mechanism of it. That's why that's why these guys from the ancient times, from the 1800s and stuff, didn't put that forward, because it's just obvious that it would refute their position. If the velocity is coming from somewhere else, then you can't ignore the reading. You don't have enough velocity to confirm the heliocentric interpretation. So that's it, or the Copernican principle, rather, where the Earth is moving at 30 kilometers a second or 66,000 miles an hour.
Yep. Yeah, that's the one important thing. One of the important things to mention here. We can start winding down, but I would like to just really quickly, just kind of like reiterate uh, that you go back to the 1800s and you look at Faraday and Maxwell and how we figured out the way that light works and the fact that light is electromagnetism. Um, they did it through the idea of knowing that there was a substantive medium that the electromagnetic waves were propagating through. Now, electromagnetic waves might be a bit of a simplification for what that is. Just simply call it a wave. But the important part is that it needs to have a medium to propagate through or to be inducted. Uh, and Faraday had to conceive of lines of force and lines of motion in order to even conceive of his experimentation that led Maxwell to derive all of his equations that showed that light to be an electromagnetic wave. But like Faraday did countless experiments, and he did it all. He found what he found, and by applying his knowledge of these lines of force and lines of motion, which mean that there's instantaneous action happening at a distance. There are things happening in quote unquote free space that mean that there is something meaningful underlying the material that we exist in. That means that there's something meaningful underlying all this, and it's not empty space, quote unquote. It's not atoms with empty space between the protons or between the nucleus and the electrons, and then empty space between all those atoms. That's not what's happening. And it's like to try and deny the ether, it means that you have to say that that's what's happening. Something like that is what's happening, that there's protons and neutrons and that it's all empty space between these things. And that's what's that that that's what's occurring. That's why they have to invoke their photons so they can have the 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 propagation of electromagnetic waves occurring in space, the light that gets to us from those stars that they say are billions of miles away, or billions of light years away, or whatever, however far they are, uh, is because they say that there's a particle that travels through all that space, but there's just emptiness between it all. Everything is just empty, right? Uh, but Faraday didn't conceive of things like that, and he wouldn't have done his experiments to figure the things out that he did if he conceived of things like that. And then when Maxwell came along and looked at all Faraday's experiments and started putting it all to math, Maxwell figured out right away that there was an ether. And he says it over and over and over again. If you go and look at his work, it's all based on studying the ether. That's what he did. That's how he derived all his equations. All of his equations that describe electromagnetism via the electric constant and the magnetic constant all comes from that understanding. So that's the backbone before we got into 1887 when they tried to measure the motion of the Earth, and then when 1905 special relativity and all this stuff, and like things to me made sense back then. Like you can actually just conceive of a reality that doesn't have to have multiple paradoxes to even be explained. And I am just going to pull up my notes real quick and read through these paradoxes. Maybe some people don't realize that if you believe in mainstream science, that you are believing in all of these paradoxes. So give me just one moment, please, and we can close out on that. I think, unless we'll do one more pause for questions. But where is this?
May I ask real quick? I'll just throw this out there. This is great conversation. I listen to you guys often. We talk a little bit. What about neutrinos? Are neutrinos, as I've heard them talked about in the electric universe model, are they part of that ether?
100%. And here's why we say that. There is a thing called neutrino interferometry, and neutrinos obey the Sagnac effect, and they claim to measure Earth rotation with neutrino interferometry. So, similarly to how we were talking about Nicholson, Gale, Pearson earlier, and they measure Earth rotation with it, right? Well, they also measured that same thing with with neutrinos. Now, obviously, we're taking the ether wind approach with a stationary Earth, but yeah, if they're all made from a primary substrate, like we assume, then they would all obey the Sagnac effect. And as it turns out, electron interferometry can measure Earth rotate, ether wind rotation, right? But I'll, just using familiar terms here. But yeah, it's all of it does. Electrons, neutrinos, neutrons, all of it. There's neutron interferometry too, dog. It's crazy.
Yeah, so all those paradoxes, right? We got the particle wave duality, which is what I said earlier, the fact that light is both a wave and a particle. There's the twin paradox, which is the whole thing. If I take off in outer space and then I come back, I'm gonna have not aged. And if I went too close to the speed of light, if I travel too close to the speed of light and I go into space and come back, then all my world has aged rapidly while I went too fast, and now I've left my world behind, essentially, right? And then you've got the Ehrenfest paradox, the Einstein-Podolsky-Rosen paradox. You've got the Schrodinger's cat, which is the cat that's dead and alive in a superposition. It's got food to eat, but the food's poison. And there's the Heisenberg uncertainty, the Newman-Seliger gravitational paradox, the information paradox. This is not my full list, but there's like six more that I'm not thinking of. But I think you guys get the idea. Um, it's literally like a paradox. There's multiple paradoxes. These are antithetical to logic. And so just, I would say that when you get to that point, you're getting metaphysical, you're getting metaphysical when you get to that point. And you're taking some philosophical leaps, and I would argue religious leaps, that maybe you should just at least understand what you're defending if you're going to defend this worldview. And you should understand now, and hopefully we have laid out to you why relativity is so important to the globe worldview, how those things go hand in hand. The idea of the earth being a spinning ball that's orbiting. Well, then you're making an assertion about relative motion, and I have yet to seen that assertion substantiated in a way that I find meaningful. And me and Alan have done our best to lay out our contentions with that assertion here tonight. Um, so I'll once again, just one final time, open the floor for any last questions or thoughts.
I think this was a really good space, guys. I know some of us love it. We tune into ether cosmology all the time, but it's cool that you're branching out in different avenues, and I, for one, can say I really enjoyed it. Thank you.
Dude, thanks for being here. Our pleasure for sure. And tomorrow night, Alan's going to be presenting about quantum mechanics, and we're going to talk about particle physics and things of that nature. So definitely tune in over at Ether Cosmology. That's going to be at 7 p.m. Eastern. We're on YouTube, Rumble, here on X. We'll be streaming, and then also check out Space Audits. That's Alan's mirror, and Shane will probably also, I think, be streaming to BitChute, Rumble. But yeah, so check us out there, and if there's no more questions, we'll go ahead and close out the stream. Thanks for
Did
tuning in, y'all. Oh, question. Go ahead.
yeah, I'm taking you back again. I got stuff running through my head. Um, undulatory theory. I've heard you say that a couple of times, and I'm not
Oh yeah.
quite.
Yeah,
Yeah.
undulation theory or whatever. That's it's just where because they first hypothesized that light was a corpuscle, right? Because that's what Newton thought. They thought like maybe there was like a little particles or whatever. But then a guy named Arago did an experiment. Well, there was a couple experiments, but Arago did like the main one, right, where he had a coherent light beam hit a sphere, and then the diffraction pattern that it makes when it recombines around the sphere, it makes a perfect little dot, like right behind it. So everyone was like, oh, okay, light's a wave. So undulatory theory just means that there's like it was the vibration theory that light was a wave. That's what solidified it for them. That was a big one for them.
Oh, okay. Yeah, I hear it, and I didn't quite understand what you were referring to. Appreciate that. Thanks.
Yeah, no worries. I put a somebody was talking about Maxwell's equations earlier. Did I tweet that or am I retarded? Oh, I tweeted it. Okay, 1 second. We'll go over this real quick and then we'll dip out. So, okay, so the way that they used to or put V in the equations when they were regarding electromagnetic waves and all that. That would be for vibrations. So vibrations equals 1 over the square of epsilon 0 and mu 0 equals the speed of light, right? So what he's saying there is the amount of vibrations that will take place in a medium in which there is this amount of magnetic permeability or permeativity, sorry, and this amount of magnetic permeability. This will be how fast, how many oscillations there'll be, right? Or how fast it'll vibrate. So they give us that 9 billion or 9 billion. No, sorry, I got the wrong one. How fast they say light is? It's like 299 million kilometers a second, something like that, almost 300 kilometers a second. So you could think about that oscillation rate in terms of 300 million oscillations per second. That would be kind of what this equation represents in a medium where there's like almost nothing, right? Where they've evacuated all the material that they can get out of it, and this is how fast they've determined the vibrations are in that medium. So this is how fast can light induct, right? Because an important part of electromagnetic radiation is that it's why is it described as an induction? Well, the electric field is inducting a magnetic field. So now they teach that the meaningfulness of that out of it in mainstream, right? There was a paper by Arnaud Deneu who covers that, but the intersection point of the electric field and the magnetic field is carried by the ether, by the charge potential. That's what allows the electric field to induce the magnetic field. There's no experimentation of an electric field inducing a magnetic field without some charge potential in between, and they ignore that in the mainstream. They just act like it just induces itself with respect to nothing. So, all right, that's it. That's all I wanted to end on there.
You know, I was thinking about a layman's way to kind of explain that. I don't know if you guys ever worked out and did this exercise called battle ropes, where you move the rope up and down to work on almost your entire body, your entire core, and the induction of the rope as it heads down. You can see how it attenuates based on how much force you put down on the ropes, and you can kind of see how that kind of relates to the light. So when you talk about the induction speed that needs to be repeated sometimes, people can kind of think of that when it comes to the speed of light. Or it's an induction rate. There's an ether there. There's something moving through that, and you don't have to think about it. BBs moving through empty space that need to adjust via velocities that need to be constant in every moving reference frame, which is impossible. So I don't know. That's a memory for me. Might not be a memory for anybody else, but kind of helps out.
No, that's what really helped me conceptualize it too, because it's just oscillation rates, right? So it's literally just vibrations, how fast something's vibrating per second. And then when you look at like this, how there's a proportional attenuation to the velocity of an observer, and it's like, well, how does that work? Well, it would just be, you could just, like, I think of it as it's just vibrating less, proportional to that velocity, right? There's just less vibrations per second. So, all right. That's everything. So check us out Tuesday. We'll be live again. I'll be going deep on quantum electrodynamics. We'll be seeing if we could find the electron and what the quantization of light even means, right? We'll be diving into that and the experimental evidence put forward to make that a positive claim or whatever. So that'll be fun. And then we'll have reading night on Thursday. Not sure if there's a subject yet, but we'll probably do something. And then Friday, of course, will be Flat Earth Fridays, hosted by Sacred and Proud. Shout out to you guys. I see you in the
Shout out level heads.
and the listeners. Shout out to the boys and the girls.
All
right.
Cool. Well, thanks everyone for being here. And yeah, see you tomorrow if you're around.
I'm gonna close out the stream. All right, guys. To those in the chat and in Twitter stream chat or whatever, thanks for coming out.